Today we're going to talk about hydraulic jumps and how we can estimate what the flow depth downstream of a hydraulic jump will be. And our learning objective for today is to use the conservation of linear momentum equation to calculate the head loss and sequent depth. So sequent depth is the depth downstream of a hydraulic jump across a hydraulic jump. And we'll start with drawing out a hydraulic jump. We'll assume a flat bed. Of course, it can have a slope. We've got flow coming in hot and fast. We'll call that Y1. And then something changes. And it could be that we have energy dissipators. And if you look at the practical engineering video that I post next to this, we see that this is a common hydraulic design, is how to design energy dissipation structures so that if we have water that's essentially coming downstream from a dam, a spillway, it's coming in really steep and fast. We don't want to erode the bed, the riverbed down here, right? So we want to dissipate that excess energy that's coming off of this. And so that could be some sort of structure there. It also could be that we're just in a natural river and the bed slope is going from steep to shallow like this. In which case we might have critical, supercritical flow coming here, and then it enters a pool and we get a hydraulic jump that happens here. So there's a lot of situations, but we'll just stick with this kind of engineered situation here. So it encounters this, we have a hydraulic jump, and then at some point downstream, we get subcritical flow. So this is supercritical. This is subcritical. And we might be able for this channel to calculate the critical flow depth. That's going to be just some constant based on the flow rate and the channel dimensions. So here's our hydraulic jump right here. And within that hydraulic jump, we have energy is lost. So if we try to do our specific energy, and we can say V1 squared over 2G plus Y1, in this case, it's not going to equal V2 squared over 2G plus Y2. So we have to add in this delta E, whatever specific energy we lost across that hydraulic jump. So because we have this energy loss, it's not necessarily something we can solve for. If we certainly can solve for that if we know what Y1 and Y2 are, that's an easy thing to solve for. But if we're designing something, we're not going to know what Y2 is ahead of time, right? Maybe we can say, well, here's our spillway. We know that we expect the water to be going this fast at this flow rate. We can calculate what Y1 would be coming off the spillway, but how much energy do we need to dissipate? What's the velocity and flow depth downstream that we want to design for? So often in that case, Y2 and delta E, these would be unknowns. So what we'll do then is we're going to turn to the conservation of linear momentum. because linear momentum is, we can say, is conserved across this hydraulic jump. And then think about how to calculate Y2 and delta E from that. So let's go over there. And we'll draw that hydraulic jump again, but now we're going to draw a control volume over it. So here is, we've got the approach flow, hydraulic jump, outflow, and we'll say our control volume is everything inside of this little prism of water. And what we're going to do then is think about the sum of forces in the x direction. And that should equal, and we've done this equation, I feel like 80 times now, rho Q V2 minus V1. And so this is the sum of forces acting on the control volume in the x direction is equal to the flux of linear momentum through the control volume. And this is under steady state conditions. So we're not going to have change in linear momentum within the control volume. All right, let's think about the forces acting on this. I'll do those in green. Haley's got her markers out. All right, I like it. Choose whatever color you want. This is going to be the force of the hydrostatic pressure force in this direction. We'll have the same over here. We've got the weight of the water. We've got some normal force of the bed pushing back up. And then we also have our friction force acting in that direction. But we're going to assume that we're going over a short distance here. So we're going to say this is negligible. And that is going to be approximation. All right, now let's think about, so those are some of forces. Now let's think about our velocities. So we've got Q, and Q coming in is equal to Q coming out. So Q is the same, and we're just going to go to our conservation of mass. A1 V1 is equal to A2 V2. And if we've got a rectangular channel, we then get V1, Y1, B. And so this is our sort of little cross section here, B, Y. Little b for the bottom, big B for the top. And that's going to equal V2, Y2, B. So we'll say the cross section stays the same. And we could use this relationship then to, we'll cross those B's out and we'll solve for one of these. So we'll say V2 is equal to V1 and the ratio of the depths, Y1 over Y2. So stick that in our back pocket for now. And then the next thing we'll look at is our forces. And if we're just looking at the x direction, we're going to look at the pressure forces. So force 1 due to pressure and force 2 due to pressure. And so I'll write that out. So F1, which is pressure, is equal to gamma some H value times area. And do we remember what that H value is? If we just have a rectangular area, it's not sloped or anything, where is that pressure force acting on? Y/2. So it's just acting on the centroid, right? So as long as we're looking at the whole water column, it's going to be acting right there in the middle. So that's what, or sorry, that's the H term that we put into this equation to calculate the magnitude of the pressure term. Great. So that's going to then be gamma y1/2 times B. So A is, A right here is going to be y1 times B. So that's our area. And so that's going to end up being 1/2 gamma B y1 squared. Shift it over a little bit. And then we can do the same for F2. And that's going to be 1/2 gamma B y2 squared. So we can take now, we'll take our sum of forces in the x direction. That's going to be force, if we say this is positive, that's going to be force 1 minus force 2 is equal to rho Q V2 minus V1. We can plug everything in there, and I'll just do that, and then we'll kind of jump to the end there. So if we put in our forces, we get 1/2 gamma B y1 squared minus 1/2 gamma B y2 squared is equal to we said Q. Oh yeah. We need to solve for Q for one of these things, right? So Q is going to be equal to A times V is equal to, we'll just put it in terms of Y1 V1. So Y1 B V1. And then we already solved for V2 in terms of V1. So we're putting everything in terms of V1. So V1, so sorry, V2 is going to be V1 times Y1 over Y2 minus V1. All right, so now we got a lot of stuff in here and we can do some things to solve. We'll note that gamma is rho G, so we can take out the rhos. We get a G there, and then we can take that out. And then we do a bunch of algebra. I'm not going to bore you with it, but what you end up having is, at some point the Froude number gets thrown in there. And I'm just going to try to find that. Oh yeah. So if you look at, if you end up with some intermediate thing where you have 1/2 G Y1 plus Y2. And here we're factoring out a Y1 plus Y2. You're able to kind of like get that out of there. That ends up equaling a V1 squared Y1 over Y2 times Y1 minus Y2. And we'll note that the Froude number is equal to V over square root of GY. And so if we see v squared, oh, sorry, we have a g over here too somewhere. Anyway, there's a g in there. So if you end up with a v squared, a y, and a g, that ends up being fruit number squared. So what you end up getting, and I'm just going to skip some steps, but I've posted these notes online. What you end up getting is y2 over y1 squared plus y2 over y1 is equal to negative, or sorry, yeah, it's equal to 2 fruit times the fruit number. And then you can end up with y2 over y1 is equal to, here's our quadratic formula, -1 plus or minus square root of 1 minus 4 times 1 times -2 fruit number squared over 2. And then solving for all of this, you end up with y2 is equal to y1 over 2 times the square root of, sorry, there's a parentheses right there, 1 plus 8 fruit number squared, and this is fruit number 1, minus 1. So this is ultimately what we're solving for. And we get y2 is called our sequent depth. It's the depth downstream of the hydraulic jump. This is the approach depth. And this is the fruit number of approach flow. So 2 knowns, these are the upstream flow conditions, and then we can use that to calculate the downstream flow condition. And I'll just zoom back up here. So we're ultimately calculating y2, which is the depth downstream of the hydraulic jump. The last point I'll make is that we can then, once we know y2, we can use the energy equation to calculate the head loss or delta E across the hydraulic jump, if that's something of interest to us. And we can do that using the energy equation. So calculating the head loss across the hydraulic jump. So if we say y1 plus v1 squared over 2g is equal to y2 plus v2 squared over 2g plus delta E, we solve for delta E, and you're welcome to do that algebra, but delta E is equal to y2 minus y1 to the third all over 4 y1 y2. And what we'll do in lab is we'll create a hydraulic jump, we'll measure the approach depth, we'll measure the sequent depth. You can then plug those 2 values in to calculate delta E. And from there, you can compare that with this predicted value. And the way we did this was we converted these velocities to Q's because the discharge is the same coming in and going out at steady state. So you get rid of those additional unknowns, and then you just end up with these 2 values.